To round out this semester, we're going to be taking a closer look at the states of matter, solid, liquid, gas, and aqueous phases. And to begin with, we'll talk about the simplest case, or the easiest to conceptualize case, gases. Gases are not confined by a container that they're placed in, and they don't have a specific shape, so that gases have neither a definite shape nor a definite volume. It is possible for us to confine a gas in some sort of environment, like, say, a balloon, and monitor changes in its volume. It's also possible for us to measure the pressure that a gas exerts. So two key measurement properties we have for a gas are pressure and volume. We've already dealt lots with volume measurements this semester, but not very much with pressure. The pressure that a gas exerts is the amount of force that that gas applies over some surface area. Typically and traditionally, pressure has been measured as a relative quantity, comparing the displacement of a liquid like mercury to some benchmark pressure, say the normal pressure that all the gases in the atmosphere together exert. This means of measuring pressure is a relative means, meaning that we can only know what the pressure of a gas is relative to something else. Therefore, it's useful if we can set some benchmark that we can gauge other pressures by. That benchmark is standard atmospheric pressure, the normal pressure of the gases in the atmosphere under typical conditions. This standard pressure is referred to as 1 atmosphere, with the unit atmosphere abbreviated ATM. Aside from atmospheres, there are lots of other ways to measure pressure. This isn't an exhaustive list, but a snapshot of some of the most common means of units of pressure measurements. We have pascals or kilopascals, millimeters of mercury, or torr, which for all intents and purposes are the same, bar and millibar, psi, pounds per square inch. All of these things can be related back to the atmosphere. And therefore, each one of these identities gives us a conversion factor to move from one quantity of pressure measurement into another. In this chapter, we will primarily concern ourselves with atmospheres when we're doing calculations. So, as an example of how we might convert one pressure unit to atmospheres, let's convert 291.4 torr into an equivalent pressure in atmospheres. This will proceed just like all of the other unit conversions we've done all semester long. We're given a value of a pressure in units of torr and asked to convert that to units of atmospheres, ATM. That means we'll need to get rid of torr and convert into target units of atmospheres. The table up above tells us what the conversion factor ought to be that relates torr and atmosphere. Here, we're told that 1 atmosphere is equal to 760 torr. To convert torr to atmosphere, we just divide by 760. In keeping 4 significant digits, as this is an exact quantity, we'll end up with 0.3834 atmospheres. So, there are many different ways to measure pressure, and as a benchmark to bring all of these pressure measures together, we will use primarily atmospheres as we move through the rest of our discussion in Chapter 9. But keep in mind that we may see any and all of these alternative pressure measures appear. What's going to be universally true is that we will concern ourselves with the characteristics of gases that include measurements of pressure and volume. In addition, other characteristics or measured values that can be relevant to gases are temperature and number of moles of gas particles. So we'll also explore those concepts. We'll give each one of these measured quantities its own abbreviation or symbol: pressure, capital P; volume, capital V; temperature, capital T; and number of moles, lowercase n. As we move through the next slides, we'll explore each of these quantities and the relationships to the others. These relationships are defined by a series of experiments that show a relationship between two of those measured quantities at a time. These relationships are thus named for the experimentalists who identified them. Boyle's law shows us the relationship between pressure and volume. Charles' law, the relationship between volume and temperature. Avogadro's, the relation between volume and number of moles. And Amundsen's law, the relationship between pressure and temperature. The first of these, Boyle's law, shows us that when temperature and the quantity or number of moles of gas particles are fixed, that any increase in pressure on a gas decreases that pressure's volume, and vice versa. So that as pressure goes up, volume goes down for a gas, which makes intuitive sense. If we applied pressure to a gas, if we compress a gas, we expect it to decrease in volume. As pressure goes up, volume goes down. Graphically, if we plotted the pressure of a gas versus the volume of a gas, we would expect an inverse relationship. So that at high pressure, up here along the y-axis, volume is small along the x-axis. At low pressure, down here along the y-axis, volume is large over here along the x-axis. These two things vary inversely, but at the same rate in their inverse direction, so that as pressure goes up, volume goes down by a concomitant amount, by some constant value divided by volume. This relationship between pressure and volume is Boyle's law. Another way to state Boyle's law is to multiply both sides of this equation by volume. And what we end up with is that pressure times volume is always constant for a gas at a constant temperature and with a constant number of particles, or moles. That means that at one set of conditions, the pressure times the volume for a gas must be equivalent to the pressure times the volume at another set of conditions. So yet one more way to write this same relationship is that pressure at one set of conditions times volume at one set of conditions is equal to pressure at a second set of conditions times volume at a second set of conditions. And this is the most familiar means by which to write Boyle's law. Here, P1 and V1 are pressure and volume of a gas under one set. P2 and V2 are the pressure and volume of the same gas under a second set of conditions. This is the first equation in a series of gas laws that will develop over the course of this chapter. So I'm going to keep P1, V1 equals P2, V2 available for the rest of this chapter for us to refer back to. Let's do a few examples of how we can use this equation. Firstly, up above, Suppose that we place some helium gas in a balloon whose volume is 44.8 liters, with a pressure of 0.5 atmospheres. We'd like to know what the new pressure of this balloon will be if we compress that volume down to 22.4 liters. So we're going to make this balloon smaller. As we make the volume of the balloon smaller, we should expect that the pressure exerted by gases in that balloon will increase due to Boyle's law. So let's apply our new equation that I've moved up here. We know that under an original set of conditions, the original pressure of the helium, P1, in this balloon was 0.5 atmospheres. And the original volume, V1, was 44.8 liters. A good means by which to solve gas law problems for this chapter is to come up with a list of all of the things that we know and try to assign them variables that match the equations that we develop. If we can do that, then picking and plugging into the correct equation is going to be easy. We know further in this problem that our volume has changed. We know a new volume, or a volume at a second set of conditions, V2. What we'd like to know something about is a new pressure, P2. Given these quantities, it looks like the only equation that we have available right now is the most applicable equation to solve this problem. Boyle's law, P1 V1 equals P2 V2. We've got a P1, 0.5 atmospheres. We've got a V1, 44.8 liters. We've got a P2 that's unknown, and a V2 of 22.4 liters. We can divide both sides by 22.4 liters to solve for P2. When we do, liters cancel out on the left-hand side, and we'll just be left with atmospheres. 44.8 divided by 22.4 is 2 times 0.5, keeping 3 significant digits, is 1.00 atmospheres. Our new pressure, 1 atmosphere, is higher than our original pressure, just like we'd anticipated through intuitive analysis of this problem. So, I'd encourage you to pause this video here and try the second problem, then come back for the solution. In the second example, we would like to know a new volume. When a gas that's held in a 5-liter balloon initially at 1 atmosphere has the pressure changed to 0.830 atmospheres. Here, pressure is decreasing, so we should anticipate that the volume will increase. Again, if we make a list of all the things that we know about, we know that at an original set of conditions, the pressure was 1 atmosphere, and the volume of our gas was 5 liters. At a new set of conditions, the new pressure is 0.83 atmospheres, but we're after a new volume. So once more, Boyle's law, P1 V1 equals P2 V2, seems like the appropriate choice for solving this problem. P1 times V1 equals P2 times V2. This time we'll divide by 0.83 atmospheres on both sides. We should keep 3 significant digits once again. Our units of atmospheres cancel out. And we should come up with a new volume of 6.02 liters. This volume is larger than the original volume of 5 liters that the gas in this balloon occupied. Just like we'd anticipated, our volume has increased as our pressure decreased. Our second gas law, Charles' law, shows us the relationship between volume and temperature. At a fixed pressure and a fixed number of moles of gas, the volume of a gas varies directly with increasing temperature, meaning that as temperature increases, the volume of a gas increases, or as a gas gets hotter, it expands, which again seems to make intuitive sense. Here, we can say that as temperature goes up, volume goes up for a gas. And in the same way that we described Boyle's law, we can also describe Charles' law. A plot of volume of gas versus temperature, like shown above, will be a straight line moving upward. The only caveat to this relationship is that the temperature at which we measure our gas must be in units of Kelvin, the SI unit of temperature. The Kelvin temperature is equal to an equivalent temperature in degrees Celsius plus 273.15. But for most good approximations, we can just concern ourselves with the plus 273. We need an absolute temperature or Kelvin temperature in order to make the math of this work properly. Because in Charles' law, the relationship between volume and temperature is direct. It's a straight line. And a straight line has an equation that looks like this. The volume on the y-axis is equal to the slope of a straight line, which is a constant value multiplied by whatever's on the x-axis, the temperature. Here, the intercept is 0, which reflects the absolute zero temperature. It is possible to have a zero temperature that's not the coldest possible temperature in the universe on a Celsius scale and also on a Fahrenheit scale. And it's possible to have negative values of temperature on Celsius and Fahrenheit scales. But the Kelvin scale is an absolute scale, meaning it starts at 0 and works its way up. Therefore, there can be no negative numbers, and 0 is only a hypothetical value on the Kelvin scale. That allows the math of this equation to work properly, because what we're going to do with this equation is divide both sides by temperature. We're going to say that for a gas at constant pressure and constant number of moles, the volume of that gas divided by the temperature for that gas is constant. We need the value in this denominator to never be 0. Otherwise, we blow up the universe. Therefore, we choose a temperature scale which can only ever be 0, hypothetically, and can never go through 0, like Celsius and Fahrenheit scales can. Another way to say this relationship is that V1 over T1 equals V2 over T2. The volume divided by the Kelvin temperature for a gas must always be constant. This is Charles' law. Similar to Boyle's law, V1 and T1 represent volume and temperature at one set of conditions, or for the original gas. V2 and T2 represent a new set of conditions for volume and temperature. So suppose that we'd like to know what temperature in degrees Celsius would be required to increase a balloon's volume from an initial value of 2 liters at 15 degrees Celsius to a final volume of 3 liters. Like in the previous examples, if we can come up with a list of variables, things that we know and things that we'd like to know, this can help us identify the appropriate equation to use to solve this gas problem. We know originally that our gas had a volume of 2 liters and a temperature of 15 degrees Celsius. So I know that V1 is 2 liters, T1 is 15 degrees Celsius. And because I'm dealing with a gas, anytime that I work with a gas, I'm going to immediately convert any Celsius measure of temperature into a Kelvin measure. To do that, I'm going to add 273. I'm going to do this straight away so that I don't forget to do it later. 273 plus 15 is 288 Kelvin. Next, I know that at a new set of conditions, the new volume is intended to be 3 liters. And we'd like to know T2. We'd like to know it in degrees Celsius. So we'll likely have one final step of extra work at the very end to get a Celsius measure of temperature. But for right now, because we're given volumes and temperatures at different sets of conditions, Charles' law looks like the most appropriate equation to use to solve this problem. V1, 2 liters, over T1 in Kelvin 288K is equal to V2, 3 liters, over T2, an unknown. And now we need to solve for a quantity in the denominator of the right-hand side. The easiest thing for us to do will be to multiply both sides by T2 so that we get rid of it entirely on the right-hand side. Now, on the left-hand side, there's a quantity that we can simply divide both sides by. If we divide both sides by this whole quantity, then 2 over 288 goes away on the left, and we'll be left with 3 liters divided by 2 liters divided by 288K. Eventually, we'll find that units of liters cancel, and we'll just be left with Kelvin temperature, like we'd expect for this problem. If we punch into our calculator 3 divided by 2 divided by 288, we end up with 432 Kelvin. Here, the temperature has increased from our initial value, and our volume has increased from 2 to 3 liters. According to Charles' law, we should anticipate an increase in temperature with an increase in volume. As volume went up, temperature went up. But we have one final step to do here. We were asked what the temperature in degrees Celsius needs to be in order to make this volume change happen. To get a temperature in degrees Celsius, we simply reverse this expression up above. A temperature in degrees Celsius is equal to a Kelvin temperature minus 273. Here, 432 minus 273 gives us 159 degrees C. This is our final answer. But notice that we could not use degrees Celsius up here and get the same result at the end. We need to use Kelvin temperatures in our Charles' law and all other gas law calculations, converting from Celsius and or to Celsius as needed at the start or end of our calculations. Similar to Charles' law, Avogadro's law shows us that as the number of moles of gas particles increase, the volume of particles increase. Or, more simply put, the more stuff we have, the more space that stuff takes up. So, as the number of particles in increases, volume increases. Another way to put Avogadro's law is that V1 over N1 is equal to V2 over N2. This expression isn't quite as useful as either Boyle's law or Charles' law for our purposes. So I'll introduce the relationship between volume and number of moles here, but we probably won't use Avogadro's law in this form all that much. And lastly, Amundsen's law, or previously as it was known, Gay-Lussac's law, shows us the relationship between pressure and Kelvin temperature. Here we see that as temperature goes up, the pressure of a confined gas goes up. Think about having a pressurized aerosol container. You always see a warning on those canisters that say do not expose to high temperature or open flame. The reason that you don't want to expose those things to high temperature or open flame is Amundsen's law. As the temperature of those gases inside a canister confined to the fixed volume increases, their pressure builds and builds until a canister can no longer hold them in. Another way to say Amundsen's law is that P1 over T1, again, where T is in Kelvin, is equal to P2 over T2. And like Avogadro's law, Amundsen's law in this form is not particularly applicable to us. But we have come up with a series of 4 laws that demonstrate the relationship between 4 quantities that measure gases: pressure, volume, temperature, and number of moles. Here are those equations again. Boyle's law. The relationship between pressure and volume for a gas is P1 V1 equals P2 V2. Charles' law. The relationship between volume and Kelvin temperature, V1 over T1 equals V2 over T2. Avogadro's law. The relationship between volume and number of moles. And Amundsen's law. The relationship between pressure and Kelvin temperature. At this point, with so many gas laws, you might be thinking to yourself that it might be useful to combine some of these into a single succinct law. And here, that's just what we'll do. And we'll give it a flashy name that's very creative in the vein of chemists. We'll call it the combined gas law. And we'll demonstrate what the relationship between pressure, volume, and temperature simultaneously are for a gas with a fixed quantity or number of moles of particles. This combined gas law is P1 V1 over T1 equals P2 V2 over T2. And this is a 5th equation that we can add to our arsenal. The combined gas law tells us how pressure, volume, and Kelvin temperature all relate to each other for a gas. So once more, temperatures must be in Kelvin, and Kelvin is a degree Celsius measure plus 273. It's not quite as direct to look at the combined gas law and predict what the effect on one variable will be given that we change 2 others. For example, suppose that we fill a weather balloon with 100 liters worth of helium, initially with a temperature of 20 degrees Celsius and at a pressure of 755 torr. We'd like to calculate the new volume for this balloon. When it's reached some altitude, it really doesn't matter that it's 10 kilometers, so that's extraneous information. All we really care about is that at that altitude, the new temperature is negative 52 degrees Celsius, and the new pressure is 195 torr. In this example, we're going to write down, just like we did in the previous ones, a list of all the information that we're given and the quantity that we're trying to find. We're told that initially the pressure is 755 torr. That's a P1. And yes, this quantity is in torr, and I said we would use atmospheres for the most part in this chapter, but torr and atmospheres aren't an offset scale from each other. They're just a ratio scale. I can measure pressure absolutely in torr or in atmospheres, just as I can measure it relatively. And therefore, because I'm going to be comparing one pressure in torr to another pressure in torr, there's really no need for me to convert pressures, just as there's no need for me to convert volumes when dealing with these 5 gas laws. Really, the only quantity that we need to be concerned about converting units for will be temperature, and temperature should always be in Kelvin. So I'm going to leave my pressure in torr. You could convert it to atmospheres, but you'll get the same result as I will at the end of your calculation, and you can try it for yourself if you like. P1 is 755 torr. This corresponds to an initial volume, V1, of 100 liters, and an initial temperature, T1, whose units I will convert. 20 degrees Celsius. I'll immediately add 273 because this isn't already in Kelvin to get 293 K. At a new set of conditions, the new pressure, P2, is 195 torr. The new volume is something I'd like to know. And the new temperature, T2, is negative 52 degrees Celsius. Once more, I'll convert it to Kelvin by adding 273. So that I come up with 221. Now, given this abundance of information, comparing pressure, volume, and temperature, we'll see that the combined gas law, P1V1 over T1, equals P2V2 over T2, is the most appropriate for solving this problem. To plug directly into the combined gas law, I'll take P1, 755 torr, multiply by V1, 100 liters, divide by T1 in Kelvin, 293 K. On the other side, P2, 195 torr, multiplied by V2, our unknown, divided by our T2, 221 K. To solve this equation, we'll multiply both sides by 221K, similar to how we solved a problem earlier. When we do that, Kelvin on the right-hand side will go away entirely. We'll be left with just 195 times V2, and we can divide both sides by 195. So we'll put this quantity in the denominator on both sides. And when we do so, we'll solve for V2. V2 ends up being equal to 221K times 755 torr times 100 liters divided by 293K and 195 torr. Units of torr and units of Kelvin cancel. We're left with units of liters at the end. And if we punch this whole thing into a calculator, we end up with 292 to 3 significant digits, liters. Our new volume is expected to be 292 liters, a quantity that we might not necessarily have deduced just by inspection of this combined gas law relationship. So we can combine these gas variables once, yes, but what about second combination? What if we wanted to relate all 4 of our gas parameters of pressure, volume, temperature, and number of moles to each other? In so doing, we can take advantage of these 5 gas laws. We know, for instance, that from Boyle's law, pressure times volume is a constant. Maybe we'll let some variable that we haven't chosen yet stand in for that constant, like R. We know from both Amundsen's law and from Charles' law that as temperature increases, pressure or volume increase. And we know from Avogadro's law that as number of moles of gas particles increase, volume increases. We can tie all of those quantities together into one singular equation that no longer shows us a change, but rather a dependence of each one of these parameters on each other. Pressure times volume is equal to number of gas particles times the ideal gas constant R times T. These four variables are tied together with a fundamental universal constant that's so prevalent that it crops up in all sorts of calculations that might not have anything outwardly to do, seemingly, with gas. This constant, R, the ideal gas constant, has a value that takes on units that are most commonly used to measure pressure, volume, number of moles, and temperature. Namely, atmospheres for pressure, liters for volume, number of moles for N, and Kelvin for temperature. The value for this ideal gas constant is 0.08206. The units are liters times atmospheres per mole per Kelvin. Liters, atmospheres over mole, Kelvin. This equation, PV equals nRT, or Pivnert, as some students like to remember it by, is called the ideal gas law. This is the crux and central idea that ties together all five of these empirical or experimentally based gas laws. The ideal gas law is pertinent and relevant to all so-called ideal gases. Ideal gases, like their name suggests, behave ideally, which means they don't interact. More explicitly, ideal gases conform to the rules of the kinetic molecular theory of gases, which we'll explore in just a few minutes. And more globally, in this course, we will only consider ideal gases, and will reserve a discussion of real gases that don't conform to these rules in a future class. Overall, though, we'll include the ideal gas law, or Pivnert, as sort of the overarching equation from which we beget all of these others. Before we move on to talking about the kinetic molecular theory of gases and how Pivnert relates to these other quantities, let's do some examples of how to use PV equals nRT, the ideal gas law. Suppose, for instance, that we wanted to know something about a gas at a benchmark set of conditions. Such a benchmark set of conditions might be referred to as standard conditions. And in particular, standard temperature and pressure, or STP for short, represents a benchmark for tabulated values. Rather than measure the properties of a gas at all possible combinations of temperature and pressure, it's convenient if we only restrict ourselves to measuring a certain temperature and a certain pressure, and then extrapolate from there. Whenever we see STP, or standard temperature and pressure, that should tell us that the temperature is presumed to be 0 degrees Celsius. And because all of our gas laws are predicated upon Kelvin temperature, that's equivalent to 273 K. And furthermore, the pressure should be presumed to be 1 atmosphere. Standard pressure is atmospheric pressure under normal conditions. 1 atmosphere. Reiterated down here. So let's determine the volume that 1 mole worth of gas occupies at STP, these standard conditions of temperature and pressure. And once more, we can make a list of things that we know. Implicitly, by being told that conditions are at STP, standard temperature and pressure, we should recognize temperature is 273 K and pressure is 1 atmosphere. These conditions aren't changing, which should signal to us that we're likely going to need to use the ideal gas law. The ideal gas law, Pivner, is the only equation in which we don't have a 1 and a 2. We have a direct correlation between pressure, volume, temperature, and number of moles, given by the ideal gas constant, R. Here, we'd like to know volume, given that the number of moles of gas particles is presumably exactly 1. From this information, we'll identify again our ideal gas law as the relevant tool to use. We're given pressure, temperature, number of moles, and a gas constant as a constant value. So we can plug directly in with all of the information provided and solve for volume. When we do so, we'll have to divide both sides by 1 atmosphere, which is trivial. All of our units, aside from liters, will cancel. And we should come up with 3 significant digits at the end of all of this. Keeping 3 significant digits, we get this answer: 22.4 liters. That means that our gas, with contents that tally to 1 mole total, occupies a volume of 22.4 liters. So, that might beg the question, what gas is this? Well, I didn't specify up above. In fact, we've rarely specified identities of gases as we've moved through this chapter thus far. All told, the identity of the gas really doesn't matter here. So far, all of these equations are universally applicable. In fact, our ideal gas law has a universal constant R already contained in it, and it really doesn't matter what gas this applies to. This is true for any ideal gas. Thus, we refer to this volume, this 22.4 liters, as the standard molar volume of a gas. In other words, 1 mole of any gas, regardless of its identity, so long as it behaves like an ideal gas, will occupy 22.4 liters worth of volume under standard conditions of temperature and pressure. And so we've come up with a laundry list of different equations that might be suitable for particular gas problems. Your job is going to be identifying which of these equations to use in a particular situation. But a shortcut that we can take is that anytime we're dealing with changes, explicit changes, like one set of conditions versus a second set of conditions, in pressure, volume, or temperature, then we're likely to need to use Boyle's law, Charles' law, or the combined gas law, and occasionally maybe Amundsen's law. When the number of moles is a factor in our gas laws, we'll almost exclusively use the ideal gas law. Rarely, on occasion, we'll use Avogadro's law. But consider that if we would like to know the number of moles of gas particles, it's almost always true that we'll take advantage of the ideal gas law, Pivner. So, see if you can solve this problem, which requires you to identify an appropriate gas law, and come back for a solution when you're done. Suppose that you wanted to bring some bottles of oxygen along with you as you summit Mount Everest. These bottles have a volume of 5.9 liters, and they've been filled to a pressure of 138 atmospheres at a temperature of 25 degrees Celsius. How many moles of gas have you placed in this bottle? And then, what's the mass of oxygen in that bottle? Consider that you're probably going to be pretty concerned about any extra added weight if you're trying to summit Mount Everest. So it might be a particular concern for you about how much your oxygen weighs. So once more, I'll come up with a list of all of the information that we know about and what we're trying to find. We know a pressure for this oxygen is 138 atmospheres. We know the volume for this oxygen is 5.9 liters. A temperature is 25 degrees Celsius, and immediately converting that to Kelvin is equivalently 298 K. And we would like to know something about the number of moles of gas in that bottle. At this point, it really doesn't matter that the gas is oxygen, because we can take advantage of the ideal gas law, a universal gas law, to help us solve for number of moles. Plug everything that we know into Pivner. 138 atmospheres for pressure, 5.9 liters of volume, is equal to number of moles, an unknown, times the universal constant, times our Kelvin temperature. To solve this problem, we'll need to divide both sides by 0.08206 times 298K. When we do that and calculate the entirety of the left-hand side of this equation, we'll see that Kelvin units go away, liter units and atmosphere units go away, and we'll be left only with moles. The number of moles to 3 significant digits ends up as 33.3 moles. At this point, if we didn't know that it was oxygen contained in the bottle, we would just say moles of gas particles. But because we were explicitly told that this gas is O2, we have an identity to attach to this gas. It's oxygen, O2. This answers the first part of our question, that the number of moles inside this bottle are 33.3. But more importantly, we'd like to know how heavy that oxygen is, what the mass of the O2 is. So to finish this problem off, we can convert what's now moles of a gas of known identity into a mass using the molar mass of oxygen. We know that oxygen, O2, has a molar mass of 32 grams per mole. 33.3 times 32 to 3 significant digits is 1,070 grams, or 1.07 kilograms of O2. Either way is just fine to express this. 1,070 grams, or 1.07 kilograms, is about 2.5 pounds. So that's 2.5 extra pounds just of breathing oxygen. Because our ideal gas law gives us yet one more means by which to get to moles of a substance, that means for us, we can do stoichiometry with reactions that involve gases. So I'm sure you are all very concerned about our ability to do stoichiometry in this chapter, but rest assured that we'll still be able to get to it. One way that airplanes generate emergency oxygen rather than carry along O2 in large flammable canisters on a plane is to create it through a reaction, say a redox reaction of sodium chlorate with iron to make oxygen, sodium chloride, and iron 2 oxide. What we're going to do is calculate here the number of grams of sodium chlorate, NaClO3, that are needed to produce 125 liters worth of breathable oxygen gas at 1 atmosphere and 20 degrees Celsius, the conditions expected inside the cabin on your nice flight. Once more, because we're dealing with gases, we're going to have to come up with a list of things that we know and those that we need to find out. Here, one of those quantities is going to be implicit and dependent upon us remembering that when in doubt in stoichiometry problems or chemical reactions, find a way to get to moles. we're told about the pressure of oxygen gas at 1 atmosphere. The volume that we need for this gas, 125 liters. The temperature at which this gas exists, 20 degrees Celsius, immediately converting to Kelvin 293 K. And because we need to know something about grams of sodium chlorate, but only have a reaction that involves oxygen, we need to be able to interconvert between oxygen and NaClO3. This requires us to do a mole-to-mole stoichiometric conversion. We need to know how many moles of oxygen we have to be able to calculate the number of moles and then the number of grams of sodium chlorate that produced that oxygen. So we're taking a leap here. We need to know implicitly that to figure out the answer to this question, we need to know the number of moles of oxygen gas. Because that's a gas, and because we know something about pressure, volume, and temperature, but need number of moles, our ideal gas law is most suitable to this problem. We can plug in what we know about pressure and volume, our ideal gas constant, and our temperature, and once again divide both sides by 0.08206 times our Kelvin temperature, in this case 293 K. When we do that, we'll find that the number of moles of oxygen gas is equal to 3 significant digits, 5.20. We've just used our ideal gas law to help us with reaction stoichiometry. Now, with this 5.20 moles of O2, it's like we're starting a stoichiometry problem from scratch. We need to go from moles of O2 into moles of NaClO3, because the only thing that we can do directly is a mole-to-mole conversion, and from moles of NaClO3 into a mass of NaClO3, because we were asked how much this NaClO3 must weigh. To do this, we're going to need a molar mass of NaClO3 to go from moles of it into a mass of it. Sodium has 1 atom, chlorine 1, and oxygen 3 atoms in this chemical formula. In total, 106.44 grams per mole. To do our stoichiometry, we need a balanced reaction. This reaction has 1 sodium on either side, 1 chlorine, 3 oxygens, and an iron. So it's already balanced. This gives us everything that we're going to need in order to convert 5.20 moles of O2 into mass in grams of NaClO3. Our first step, marked in green up above, is the conversion of O2 into moles of sodium chlorate. We need to convert moles of O2 into moles of NaClO3. For this, we use coefficients from our balanced reaction. Our coefficient in front of oxygen is 1. Our coefficient in front of sodium chlorate is 1. Next, we'll need to convert what's now moles of NaClO3 into grams of NaClO3. For this, we'll take advantage of the molar mass we just determined, 106.44 grams in every 1 mole. As we multiply all of this through, we'll be left with grams of NaClO3 at the end. To 3 significant digits, the mass of sodium chlorate ends up as 553 grams. And just like that, we've found yet one more means by which to do stoichiometry. If we can get to moles and we have a reaction, then we can carry out stoichiometric calculations. So rejoice, because this is so much fun. Know that the ideal gas law pertains only to gases. So we can only apply the ideal gas law to the only gas that's present in the chemical reaction up above. And from that gas, we can perform the rest of the stoichiometry associated with the reaction. All right, so let's take a break from stoichiometry and calculations and talk about some theory and concepts. I mentioned earlier the kinetic molecular theory of gases. Here we're going to explore the 4 postulates of this KMT, kinetic molecular theory. Postulate number 1 of this theory that defines ideal gases says that ideal gases consist of point particles. These particles have negligible volume, so they take up a minuscule amount of space, but that they move in constant, rapid, random motion. So gas particles are in constant motion, but they're just little tiny point particles that really don't amount to much. Secondly, these particles are so small with respect to the volume that they occupy that gas is mostly just empty space, sort of like an atom is mostly empty space. Anytime that these tiny little point particles do hit each other, though, or collide, those collisions are elastic, meaning they don't transfer energy to other particles or to walls of their container, so that these particles remain in motion and aren't bogged down by things like attractive or repulsive forces between particles. Lastly, the average speed with which these particles move determines their absolute temperature. Temperature is directly related to the average kinetic energy of a group of gas particles. The 4 empirical gas laws, Boyle's, Charles', Avogadro's, and Amundsen's, can all be explained under this kinetic molecular theory. In order to explain all 4 of those gas laws that were based on experimental evidence in the vein of this theory, we'll think about a closed container like an aerosol can with a gas inside of it. We can imagine pressure, which is force applied over some surface area, like, say, the walls of a canister. Pressure is a result of gas particles moving in constant motion, and therefore, just by sheer statistical coincidence, eventually hitting the walls of their container and applying a force to those walls. If we decrease the volume of that container, if we make a smaller and smaller canister, if volume decreases, then the likelihood of bombardment with the walls of the container for any given gas particle goes up, and therefore pressure goes up. This explains Boyle's law. As volume decreases, pressure increases, and vice versa. Secondly, if we imagine our container at a set constant volume, increasing the number of moles of gas, or just increasing the number of particles of gas inside, would mean that there are now more particles and therefore a higher likelihood of particles bombarding the walls of the container. Pressure would go up. Or, alternatively, in order to keep pressure the same, we'd need to make the volume bigger to be able to equivalently house, at an equal pressure, a larger number of gas particles, so that as number of moles goes up, volume goes up. Avogadro's law. Lastly, if we increase the temperature for a set number of particles inside this canister, because temperature is related to the average kinetic energy of particles, the force with which particles hit the walls increases. And pressure goes up. Hamilton's law. Or, to maintain a constant pressure, we need a bigger volume container. Charles' law. This last idea is the most applicable to us for thinking about chemistry. So, as temperature goes up, according to the kinetic molecular theory of gas, the average kinetic energy of particles increases. And although kinetic energy is the real central focal point of this idea, we can tie kinetic energy to a speed or average velocity instead. If you've taken a physics class, you might know that kinetic energy is equal to 1/2 mv squared. That's 1/2 times mass times velocity squared for a moving object. So we can say that if kinetic energy is increasing for a particle with a constant mass because it's not reacting, the velocity of that particle must be going up. So as temperature increases, the mean speed of a gas particle must be increasing. Or, if we have a distribution of particles with different masses, we can also say that at a constant temperature, because all of these particles have the same average kinetic energy, regardless of their mass, at a constant temperature, in order to compensate or overcome for mass differences, particles that are heavy must move slow, and particles that are lightweight must move fast. This also maybe makes some intuitive sense. The heavier something is, the slower it moves at a constant temperature. The lighter something is, the faster it's able to move. This means of comparison from the kinetic molecular theory of gases allows us to predict how fast a particular gas particle is likely to move relative to others at a constant temperature, given its overall molar mass. For example, if we compare the average speeds of oxygen, nitrogen, water vapor, helium, and hydrogen gases like you see in this plot here, we see that the average molecular speed, which is the peak of any one of these distributions, is farther and farther out along the x-axis, the lighter some gas particle is. Hydrogen, which is the lightest of these molecules or atoms of gas with a molar mass of 2, has a peak in its distribution of speeds way out here at a really high velocity. Oxygen, O2, with the greatest molar mass of 32, has a peak in its velocity distributions that's at the lowest point along this x-axis. So we can generalize this and say, similarly to the previous slide, that the greater the molar mass of a gas particle, the slower it will travel on average at a given temperature. This relationship allows us to do something like rank the relative speeds of gases. Here in this example, we're going to compare hydrogen, carbon dioxide, argon, sulfur hexafluoride, uranium hexafluoride, and krypton gases, all of which are at the same constant temperature, through comparison by relative speeds. To do this, let's come up with a list of all of the corresponding molar masses for these gases. I'm going to have a table that lists the gas, the molar mass of that gas, and then eventually a rank for speed. So you might want to take a few moments and fill this table out for yourself, then come back and see the results. All right, let's fill in molar masses. I'm just going to do to the ones place. So I'll say hydrogen has a molar mass of 2 for all intents and purposes. Carbon dioxide, a molar mass of 44. Argon's molar mass is 40, SF6, 146, UF6, 352, and krypton, 84. In terms of rank, we expect that the heavier a particle, the larger the molar mass, the slower that gas particle moves. So we should expect that the heaviest particles are the slowest. UF6 is the heaviest, largest molar mass of this group. This is going to be the slowest, or if all of these gases were in a race, this would finish sixth. So which finishes first? Which is the fastest? Well, it stands to reason that the lightest particle must be the fastest. Since hydrogen is the lightest of the gases on this list, we'd expect it to come in first in a race. All of the rest of the gases will follow in order of molar mass. The second lightest is argon, next carbon dioxide, then krypton, second to last, second heaviest, is SF6. And thus we can rank comparatively the speeds of these 6 gases. That concludes Chapter 9 and our discussion of gases, which overall really isn't too bad. Our main concern is identifying appropriate gas laws to use. After we've discussed gas laws, we talked about comparing gases on the basis of speed using the kinetic molecular theory of gas. Next, we'll cover other phases of matter, liquids, solids, and solutions.